on reductions of discrete integrable systems.
Now I can speak. So I have microphone. It's quite new and it has the same stick as 3 years ago. So we can. Okay. So I'm going to speak about discrete Painlevé equations and Painlevé correspondences. So this is maybe the new thing is correspondences. Yes, and there is a joint work with Pavlos and Kasotakis and James Atkinson somehow, and it is thought to be an also introduction to the next talk. Yes, and okay, because somehow the new things are reductions on some equations, and okay, the main author is Pavlos, and I am here because it needs some introduction, and I am in the common intersection of all these papers, and these papers are just the results of the program. So I would like to thank the organizers of the program because it's a really extraordinary event, and we know it. So this will be the introduction. So the talk consists of 2 parts. So the introduction, so the things we have done so far, and then will be the main point. But the main point is, are similarity reduction in pretty standard procedure, and there are just some of papers. You can find them, yes. And we take advantage of this effort, but there will be some new ingredients. Yes. So to start with, I would like to go deep in the past. So just to work is Estabrook paper. Yes. So because in this paper we have the potential KdV equation, yes, which is written here. And it's Backlund transformation, yes. This part is Backlund transformation with parameter K1 for this equation. So what is important for us is this equation. Not equation yet. Yeah. But then we can compose 2 such a Backlund transformations with parameter K1 and K2, and we obtain Bianchi permuttability diagram for a potential KdV equation, or nonlinear superposition principle for the potential KdV equation. Yes, so this is standard thing. So this is 1973. You can have this equation, and then of course you can. Now we know we can recognize this equation because you can reinterpret the Backlund transformation as an additional discrete variable. So okay, and it originates. The statement originates from this equation. So some words about notation. So I'm going to. So Backlund transformations now is a new discrete variable, and you get this nonlinear superposition principle for the potential KdV equation becomes a discrete 2-dimensional discrete system on Z2 lattice, and we call it now lattice potential KdV equation. There are some things to be done. So there are 2 parameters. One is the function of m, the second is function of n. But I will just write it P and Q. Yes, but then the standard tricks is when you have potential KdV equation, then you have this red equation in the Backlund transformation. Then you can introduce a new variable, just new variable, and you obtain just standard KdV equation. So that's why it's called potential KdV, the previous one. Yes, and you have the green relationship. So from that equation, you have this green relationship. And you can rewrite this superposition principle. Okay, from that you can derive such an equation. Yes, so this is nonlinear superposition principle for KdV equation. And there is Adler and Veselov who noticed, but that it is the problem is it is quadratic. Yes, it is quadratic in y1, 2, for instance. In each variable, it is quadratic. Yeah, it's okay, but it's still. Yes, we believe it's something that is integrable. Yes, that whatever we take. So, okay, so we discovered it later, but we arrived to this equation from a quite different point of view. Okay, just I will call this. We will use the word correspondences whenever you have problem with when you have initial data and you want to calculate y1, y2, and you want to calculate y2, and you have problem with branching, I will use the word correspondence. Yes, and there is standard things, okay, because it's somehow related to the Kozlov-Schofield classification. In the continuous case, it is somehow related to the classification of differential equations of the second order, second degree. Second degree is important here, equation. So now we have more or less similar situation, but it's more difficult, different, yes? So this is classical example that we have discrete CKP equation. It's again quadratic in tau 1, 2, 3, for instance. Okay, so but now some procedures. Yes, so when you have lattice potential KdV equation, you can find the you can find. Okay, you can see that it's translationally invariant. So this is the symmetry of this equation. Yes. And symmetry of this invariance are these u and v functions. So it is good to see this. So this is the fields this is the field, and which is attached to the vertices of the lattice. But that one, it is good to think about them as attached to bonds of the lattice, because you have this, they connect to points. Yes, so we have some fields which are related to the bonds of the lattice. And then you can rewrite this equation in terms of these two invariants, and you get this additional equation, this new equation. So now it's, let's say, first order, but so let's say vectorial version of this equation. Yes, so we have two fields, u and v. And well, and I'm going to focus on this equation. There is a way to go from this equation, let's say, to a map. Just map from the pair u and v to map u, capital V, just by identification that v1 is equal capital V and u2 is capital U, and you obtain a map of this one. Of course, it is not the first paper, because this is just some results from Papageorgiou, Tongas, and Veselov. But of course, the very beginning of that story. So please remember just from this slide, this picture that we have. I will going from the lattice to the map and map to the lattice very frequently. So this is important, yes, for me. But of course, the source of that is in paper by Adler, Bobenko, and Suris. They produce a F-list of the Young-Baxter maps. And very important from the point of view I am talking is the comments in the paper 2003, this famous ABS paper on the classification of consistent Adler cube equations. Yes, and then I'm going to use again the same, because more or less these maps F5 and CH5, the previous one, are more or less equivalent in some sense, but I not going to go into the details because I have no time, but it's just, we sometimes use this one, sometimes this one, but in principle they are minor things that they differ in mathematics. Okay. What is very important that this map, for example, F5, is involution. So, and because it is involution, so it has plenty of integrals. And very important for us is to find integrals or alternating integrals, so minus is here, yes, in a special form, separated form, so the variable separates. And there are just three spanning integrals of this form. So we prove that there are only three such integrals, and that the just general integral then is separated. In this case, alternating integral is just this integral. And then again, the h is very important. I will write h because this a factor. So, okay, integral is important. Integral in separated form is even more important. Yes, because first of all, when we go to the lattice, so from this picture, from this map, when we go to the lattice, it turns out that this integral, so we have the equation, and but it's for CH5. Okay, yeah. So, anyway, we have three-parameter family of potentials. Let's say so. We have so you can due to the fact we have this integral, we can introduce two potentials, potential psi, and there are several parameters a, b, and c. There was d, but we replaced d with alpha 1 minus alpha. And it looks strange, but it will turn out to be fruitful to have this artificial alpha in the story. So this is the progress. So now let me see for the particular cases. When c and b is equal to 0, so we have in the previous slide, we have a, b, and c, and the function alpha. When c and b is equal to 0, then let's call psi equal x, and then we have lattice potential KdV, and this artificial term, which for instance very frequently appear in Frank's talk, but particular alpha. And I asked once Frank, why do you keep this artificial term? Because the limit is the good one. You have the full dp1, dp2, and not just with the one missing constant. That was the answer 6 years ago to Frank. So let's keep this artificial alpha, because you can remove it from this equation. It's by introducing x minus alpha. Then, okay, then when you take the next case, a equals c equals 0, then you have this sort of equation. And this is this nonlinear superposition principle for the KdV equation. So this quadratic one for this case. But there is the third case, and we have problem with this case when a and b is equal to 0, for instance. Then you have equations. When you eliminate u and v from these equations, you obtain 9th degree equations in each variable. And the problem is we are not sure whether you can factorize this equation. So we don't even know, because maybe it factorizes in something. It's not a perfect cube, definitely, but maybe it factorizes. But so far we have a huge equation, several pages of output, and we don't know what to do. But of course we can keep it like that. Instead, I want to show you just because this is a particular case, because we have to just solve this cubic equation. So we can consider the real case. Just everything is real now. Yes, so all the functions are real, and assume that p and q are negative. Yes, in this case. Yes, and p and q are negative. I hope yes, it will be negative. Then of course you can solve u and v, and these square roots are just arithmetic square roots. So this is the only real solution. and you have the map. Yes, U and V are defined in this way, and you have the map, the standard map, and this map, the equation, and this equation is consistent around the cube. You can okay. Then you have plenty of more examples, but I just use the next one. Then you have another one. Now you can do it multidimensional case, but so I is now 1 and 2. Let's say focus on this case. Two cases, and you can have some more general equations which are not even algebraic, but they have exponential function here. So you can, that one is invertible. It's just by bijection. Yes, if you assume that parameters are confined. Yes, so there are special. So you assume that the parameters are in this range. So then this is bijection, and you have this sort of map. And again, this one is consistent around the cube. I am talking about the real situation. Yes, this is real. Yes. So then, of course, we have plenty of examples, but then James appeared, of course, with some nice ideas. So we have this nonlinear superposition principle for the KdV equation, and of course, when you ask student, when you give student a second degree equation, polynomial equation, then she gave it back to you the discriminant of it, no matter what is the question. Yes, so yeah, so yes, but of course in this case, okay, it was very important because this discriminant for this equation looks like that. So, and it was just James' idea that okay, so we have nice structure here. So we have 2 biquadratics, just the same biquadratics here, here, yes, and let's try find for this discriminant the equation itself. Yes, and then just change the biquadratics, and then you are able to produce the equation. So we spent some time in Australia with bats and possums and so on, and we produced a list of such equations that just with the discriminant of this form. And again, in a sense, because it needs to be, should be more precise that they are consistent around the cube, but that should be, I should be more precise. I am not going to talk about that because I have to talk about the main ingredients. Okay. So, and James will say something about that. Yes. So look at the discrimination. So this is somehow you can replace this term also with something which is more general, more symmetric. Yes, there are 2 B's. In the next one, there will be perhaps talk will be 3 B's. But now I have to talk about this. Is okay, just introduction. Then, so some more quadratic equations. But that is completely new. So it's not. We were not able with Pavlos to get this equation. So it comes from this new procedure. But then standard thing somehow. So we have this system. I will call it superior system. So it's above this potential system. So we have. So I treat the field equations as the superior, but the potential as less important. But of course, it's not the point. And then try to impose similarity constraint. The standard story. Yes. So you assume that. Functions shifted in, let's say, second direction and then twice in the first direction should coincide. So we have this periodical reduction of the story. And there is the new thing. The one message I want to give you as a new thing is this point. Yes. So and then try to find the results in terms of the function h, which is of this function, which is just integral. I showed you a couple of minutes ago. Yes, then because usually when you do such a reduction, so from this okay, from lattice potential dV. Okay, in principle, at the first step you obtain higher, let's say, third order difference equation. But when you deal with the H, you end up with the second order. So this is some sort of advantage. The equation is simpler. So, and two examples, of course, when you put B equals C equals 0, then you have, let's say, Painlevé 1 or Painlevé 2 in the full. So nothing to do. Just no additional assumption. Just do this reduction, and as an outcome, you have full Painlevé 2 equation. Yes? Yes, so S is just the new variable, m plus 2n, because all the functions should be the function of this variable. Then, you can do the case, this quadratic case, and again you obtain something which is now quadratic. So I would like to call it quadratic or correspondence, Painlevé correspondence, or so, because it's just reduction of the integrable system, let's say. Yes, just to compare it with the known results. So we take paper Ramani Grammaticos Joshi about second degree, second order equations or correspondences. Yes, so we assume that Q is quadratic in x1 and it's quadratic x minus 1. And there are several examples in this paper. But what is the common feature for this? That there is a relation between discriminants. The discriminant with respect of the Q with respect x1 is just the same discriminant by shifted by minus 1. And it's very helpful. But yes, so this threat is just very important. And then, of course, in our case, we have slightly more difficult situation, and we don't know what to do. So these discriminants still are related. So this is shifted. This factor, it factorizes. This factor is shifted by 2. Yes, yes. And then just by 1. Yes, and several procedures we are able to do in the previous case. We are not able to do it in this case, and I think it's interesting. Yes, let me go to the next paper, hierarchies. Because there was a paper by Phil Joshi and Frank Neal. They advertised some results, and the results never appeared. So perhaps Chris is no longer in the then. So we did some work on this business, and in fact it's also closely related to this paper with Cleo Creswell and Nalini as well. So I show you some advantages. Of course, okay, it's not all the papers we just want to show, but these two are very important because we are using the procedure of this paper in principle. Yes, and you get the hierarchy of the equations, and the first member of this hierarchy. So you have hierarchy here. Yes. Yes, maybe I should explain the notation, but I can explain you later. So the first member of the hierarchy is, so we have two cases, odd, even and odd cases. Yes, so for the odd, you obtain, let's say, P1 or P2 hierarchy. Yes. So this was known to Nalini. Yes. But then for the odd, we have alternative of discrete Painlevé equation. So still is the same procedure. So nothing changed. Yes, we applied just permuttability, this similarity constraint, and this is just straightforward calculations, and the outcome is the full versions, and the lowest equations are yes. And I think also it's new, but perhaps it's in Frank's shelf, but he has told me, because I tried to find this thing, but if somebody knows this result, please let me know. This is the next outcome, that you have slightly more than usual, maybe, yeah. And conclusions. So I still insist to to treat the so from Young-Baxter or general involution equations we came to the standard lattice equations and not only equations but also correspondences. So we said because due to that fact we have Backlund transformation between correspondence and between let's say standard integrable systems and correspondences. That's why we claim they are integrable, because we have just procedure to transform the solution space of the one equation to solution space of the correspondence. But of course there is still problem with branching. Nothing changed. And then then still I've seen somewhere that a comment that already Faddeev long time ago said that Young-Baxter maps are very important in integrable systems. Yes, but I never. I try to find this comment somehow, and then I try hard to I scroll down the Faddeev papers, and I haven't found any trace of the yes, but maybe somebody is aware. So I am trying to tell that Young-Baxter are important things. Sorry. No, it was Faddeev. Yes, that's no Drinfeld. Okay, yes, Drinfeld. Okay, yes. No. Exactly. Yes, but maybe somebody who wrote this note made the mistake. Yeah. Yeah. But then I have problem. Okay, and then the final story is that So we try to convince that the message is to that these bond systems are somehow very useful. That's not to say a very big word. That's very useful. So they can help us to include correspondences into the integrable business, because there are just superior equations, and there are beyond them there are standard integrable systems and correspondences. We did the problem of branching. Yes, and yeah, that's it.
Your correspondence Painlevé equation, did you compute the continuum limit?
I have this question second time in a row. Yeah. No. Yeah, Robert Comte asked me a week ago. Yes, exactly the same question. Yes, yeah. For tomorrow, let me homework. Yes. Yeah.
So if P and Q are related to N and I, non-autonomous case is also valid.
Sorry?
Are these results valid for non-autonomous case?
Non-autonomous. P and Q is function of M, Q is function of N. It's standard story in our business. So we know it from a long time ago. Yes. I think from IBS paper, more or less, you can infer it directly. So, yeah.
So is it possible to derive the discrete Painlevé equation with higher symmetry with direction?
In principle, yes, but well.
For example, is it possible to derive a QP6 or B1 with P15 symmetry? For example.
But from a different equation. So I think it's already done by Chris Omerot. Yes. So well, it's you can derive QP6, but the question is what about above QP6?
Yeah. For example,
yeah, but then
E-type.
Yeah, but then A-type is okay. It's the problem. No. For E-type we don't know. Yes, because all we have is just list of maps by Adler-Boolean-Cohen series. So and it's not enough. Somehow.
List now as well.
Sorry.
You have Yama's a new list now.
Yes. So well. Sorry. Okay.
More components.
Multi-components, yes, but I don't know if multi-components is helpful somehow, but
Yeah.
yes, but you think so?
Well, okay.
Why do you call them superior?
Why not? Yes. Okay. So because you can, in physics, for a long period of time, the potential was not superior. Superior was the field equations. But we know Aharonov-Bohm effect. Okay, so I provide you that maybe not. But the point is, they help to handle with the the correspondences. So it's just you have the superior equation and several incarnations of this type. The one is the standard lattice potential KdV, and the other are just the same the potential version of the same object.
Okay, let's thank our speaker.